More than 200 billion stars populate our galaxy. Many of them are billions of years older than our own sun. If even a slim portion of those stars gave rise to intelligent life, the galaxy should be absolutely packed by now. Signals crisscrossing the void, visitors, colossal structures blotting out starlight. And yet, when we tune in and listen, we receive nothing back. Pure silence. Tonight, we walk through 30 of the strangest, most chilling ideas science has ever conjured to account for it. If this resonates with you, hit like and subscribe. Now, breathe in. We are heading into the dark. It began over a meal. The year was 1950. A gathering of physicists at Los Alamos National Laboratory had sat down for lunch. Among them was Enrico Fermi, one of the most formidable intellects of his era. The man who helped construct the world's first nuclear reactor, a Nobel laureate, a towering figure in modern physics. The mood at the table had been relaxed. Someone mentioned a recent newspaper cartoon depicting aliens pilfering trash cans. Laughter went around. Then conversation drifted toward flying saucers, which were all over the news at the time. A few quips, a few ideas, and then, right in the middle of the meal, Fermi fell silent. He glanced around the table and posed a deceptively simple question. Where is everybody? His colleagues set down their forks. They understood instantly what he was getting at. The galaxy holds hundreds of billions of stars. Many of those stars have been burning for billions of years longer than our own. If intelligent life had taken hold on even a modest number of planets, some of those civilizations would have gotten an enormous head start. We are talking millions, perhaps billions of years of additional development. That is time enough to cultivate technologies beyond anything we could conceive. Enough time to spread through the galaxy many times over. And yet, nobody has arrived. No signal, no probe, no relic on any moon, no inexplicable structure dimming a distant star. Nothing. Fermi ran the rough arithmetic in his head. The figures refused to add up. Even with cautious assumptions, the galaxy should be teeming with civilizations. Some should have claimed entire star systems by now. Some should have dispatched self-replicating machines that fan outward from world to world. Given sufficient time, those machines alone could have charted every corner of the Milky Way. Yet nothing is there, or at least nothing we can detect. That brief question, posed so offhandedly between bites of food, became one of the most profound unsolved problems in all of science. It eventually acquired a name, the Fermi Paradox. The word paradox deserves attention here. It does not simply mean mystery, it means contradiction. The mathematics insists they should exist. The observable evidence says they do not. Both propositions cannot hold simultaneously. And the chasm between what we expect and what we find has nagged at scientists for over 7 decades. Here is what makes it so deeply unsettling. It is not hard to imagine why one civilization might crumble. Conflict, illness, bad fortune. Sure, but the paradox is not about one civilization. It is about all of them. Every conceivable species on every conceivable world across billions of years of cosmic history. For the galaxy to be this hushed, something must be halting each and every one, without exception. That thought alone ought to rob you of sleep. In the decades since that lunch, hundreds of scientists, philosophers, and visionaries have tried to untangle this mystery. They have generated theories that span the spectrum from coldly rational to absolutely terrifying to utterly mind-warping. Some contend that we are alone. Some say they are concealed. some argue they came and went before we were watching. And some suggest the answer is so grim that we should pray we never learn it. We are going to move through all of them, one by one. And what waits deeper in this list will make the opening ideas feel almost cozy. Before we can appreciate why the silence is so jarring, we need to understand why scientists expected noise to begin with. In 1961, a young astronomer named Frank Drake took a seat at the National Radio Astronomy Observatory in Green Bank, West Virginia. He had just convened a modest group of scientists to wrestle with one enormous question. How many intelligent civilizations might currently exist in our galaxy? To frame the discussion, he sketched out a formula on a chalkboard. It was never designed to produce a definitive number. It was designed to break the problem into manageable pieces that could each be studied in turn. That formula became known as the Drake equation. The logic runs like this. You begin with the rate at which new stars form in the galaxy each year. You then multiply by the fraction of those stars that host planets. Then by the fraction of those planets capable of supporting life. Then by the fraction where life actually emerges. Then by the fraction where that life achieves intelligence. Then by the fraction that builds technology capable of broadcasting signals into space. And finally, you multiply by how long such civilizations remain detectable before falling silent. Each factor looks plausible on its own. And that is precisely what makes the resulting figure so astonishing. Even using conservative inputs, the equation implies there could be thousands of civilizations in the Milky Way at this very moment. Some estimates run far higher, tens of thousands, hundreds of thousands. The galaxy should be buzzing with transmissions, signals ricocheting between stars, beacons pulsing from distant worlds, evidence of construction on scales we can barely picture. And yet, every time we swing our telescope skyward, we are met with silence. Here is the problem, though. The Drake equation is only as reliable as the values you plug into it, and the honest truth is that we are estimating most of them. We have a reasonably firm handle on stellar birth rates. We now know that planets are extraordinarily common. The Kepler Space Telescope alone confirmed that virtually every star in the galaxy hosts at least one planet. That was a revelatory discovery. It tells us that the raw building blocks for life are distributed everywhere. But the later variables in the equation are where confidence evaporates. How frequently does life ignite on a world where the conditions permit it? We have exactly one example, Earth, and we do not fully grasp how it happened even here. How often does life ascend to intelligence? Again, one example. How long does a civilization persist once it has raised radio towers and split the atom? We have no idea whatsoever. Those unknowns function like cracks in a dam. Shift any one of them slightly, and the entire calculation floods in a different direction. Dial them low enough, and the galaxy transforms from a bustling metropolis into an empty cemetery. Dial them high, enough, and we should have neighbors within shouting distance. Drake himself never claimed the equation delivered a final verdict. He described it as a way of organizing our ignorance, a map of everything humanity still needs to learn. And that is what gives the Fermi Paradox its enduring bite. Because even the most elementary version of the math keeps pointing the same way. They should be out there, so where did they all go? The answers that follow will attempt to account for the silence, and some of them will get under your skin. Let us pull back the camera for a moment and think about time. Because when you truly absorb how old this galaxy is, the silence stops being puzzling and starts being almost suffocating. The Milky Way is around 13 billion years old. Our own star and planet coalesced roughly 4.5 billion years ago. That means the galaxy had already been forming stars, nurturing planets, and stirring chemistry for over 8 billion years before Earth even existed. 8 billion years. Sit with that. Human civilization as we know it stretches back perhaps 10,000 years. Modern technology, the kind capable of reaching across interstellar distances, has existed for roughly a century. On cosmic scales, we are infants who have only just cracked open our eyes. Now, picture a civilization that got going just 1% earlier in the galaxy's lifespan. That translates to about 130 million years. What would they look like today? Consider how dramatically humanity progressed in just the last few hundred years. We moved from horses to rockets, from candles to lasers, from ink-stained letters to signals that propagate at the speed of light. Now extrapolate that trajectory across 100 million years. The result is something that demolishes the imagination. A species that old would not merely have mapped the galaxy. They would have re-engineered it. They could have wrapped structures around stars, repositioned planets, and left behind fingerprints visible from a million light-years out. And it deepens from there. Some stars in the Milky Way are nearly as ancient as the galaxy itself. Planets formed around those stars billions of years before ours did. If life kindled on any of those primordial worlds and climbed to intelligence, the lead they accumulated is beyond verbal description. We are speaking of civilizations that could have risen, collapsed, rebuilt themselves, and dispersed across a million star systems, all before our world was anything more than a drifting cloud of gas and dust. So where are the remnants? Where are the ancient probes coasting through interstellar space? Where are the energy networks enveloping distant suns? Where are the signals, even the ancient, attenuated, accidental ones? There is a concept in this field known as the colonization timescale. Researchers have calculated that even with sluggish vessels, craft moving at just a small fraction of the speed of light, a single civilization could claim the entire galaxy in somewhere between 1 million and 10 million years. That sounds immense. Against the backdrop of the Milky Way's age, it is an eye blink. That window fits inside the galaxy's history thousands of times over. This is what hones the paradox to its sharpest edge. We are not asking why we have not personally bumped into any aliens. We are asking why, across billions of years of opportunity, we find not a whisper, not a footprint, not a heat signature, not a ruin from any civilization of any era in any direction. The universe possessed the time. It had the ingredients. It had the space. And it appears untouched. Something is profoundly wrong with this picture, and the theories we are about to examine will try to name what that something is. Some of them reach back into the past. Others reach forward into our future. And a few of them aim directly at us. Before we begin assigning blame for the silence, we need to genuinely appreciate just how vast the search territory is. Because, when you confront the true scale of the problem, you will understand why some scientists argue we have barely scratched the surface. The Milky Way spans roughly 100,000 light-years from one edge to the other. To frame that concretely, light itself, the fastest thing known to exist, requires 100,000 years simply to cross from one side to the other. If you were to somehow drive a car at freeway speed without stopping, the same journey would consume over 1 trillion years. 1 trillion. Numbers that large stop carrying emotional weight. Within that disk sit somewhere between 200 billion and 400 billion stars, each one a furnace blazing in the dark, most of them encircled by worlds. Thanks to programs like Kepler and the Translating Exoplanet Survey satellite, we now know that planets are not exceptional. They are ubiquitous. Every star in the galaxy hosts at least one on average. Some host 5, some host 8. The total count of planets in the Milky Way is almost certainly in the trillions. And here is the detail that should stop you cold. We have examined a laughably tiny fraction of them. The most exhaustive radio survey for extraterrestrial signals ever undertaken was conducted by a program called Breakthrough Listen. Even with all their resources and determination, they have swept only a sliver of the sky. One astronomer likened it to drawing a single cup of water from the ocean and declaring there are no fish. Now, consider how many of those trillions of worlds occupy the habitable zone of their stars, the orbital band where temperatures permit liquid water. Current estimates place the number of such planets in the Milky Way in the billions. Billions of locations where, in principle, chemistry could tip over into life. And yet every time we open our ears to the cosmos, we hear static. There is another layer that makes all of this even more humbling. We have only possessed the ability to detect radio signals for approximately a century. Our detection equipment is primitive by any reckoning. We sweep a narrow slice of frequencies. We concentrate on a handful of nearby stellar neighbors. We hunt for patterns that mirror our own technology. If an alien civilization uses a communication method we have not yet invented, we would miss it entirely. The experience would be something like pressing your ear against the soil and trying to eavesdrop on a conversation happening over the internet. Some researchers insist that the Fermi Paradox is not a paradox at all. They argue it simply reflects the limitations of our own search. The silence, they say, is not evidence of absence. It is evidence of how little we have actually explored. That point is fair and even somewhat reassuring, but it only stretches so far. Even with our clumsy instruments, certain things should still be detectable. A civilization tapping the energy of an entire star would radiate waste heat visible from across the galaxy. A species erecting megastructures would cast shadows detectable in starlight. And a truly ancient civilization, one with millions of years to propagate, should have left imprints that even a fledgling species like ours could stumble upon. We see none of that, and that is where the genuine fear sets in. On a warm August evening in 1977, something happened that still unsettles astronomers today. A radio telescope called the Big Ear, operated by Ohio State University, was conducting a routine sweep of the sky as part of an early extraterrestrial intelligence search. It was an enormous instrument, roughly the footprint of a football field, quietly logging the ambient noise of the cosmos. Most evenings brought nothing eventful. Static, background hum, the expected emptiness. Then, for exactly 72 seconds, the telescope registered something else entirely. A powerful narrowband signal streaming in from the direction of the constellation Sagittarius. It was strong, strikingly so. It fell near a frequency of 1,420 megahertz, which corresponds to the natural emission of hydrogen. Scientists had long identified this frequency as a rational candidate for interstellar communication, since hydrogen is the most abundant element in the universe. Any civilization with even a rudimentary grasp of astrophysics would be aware of it. The signal climbed in intensity, crested, then tapered in a pattern precisely consistent with a fixed point source drifting through the telescope's beam as Earth turned beneath it. It behaved exactly as a signal originating from deep space would be expected to behave. A few days later, astronomer Jerry Amon was reviewing the printed data readout. When his eyes landed on the anomalous string of characters representing the signal's amplitude, he reached for a red pen, drew a circle around them, and in the margin beside them wrote a single word. Wow. That word became the signal's permanent name, and it became a legend. Here is why the discovery mattered so profoundly. The wow signal satisfied nearly every criterion scientists had articulated for what a genuine alien transmission might resemble. Its frequency band was narrow. It originated from deep space. It occupied a channel with compelling scientific logic behind it, and its intensity dwarfed the surrounding noise by a wide margin. But a devastating problem emerged. It never repeated. Amon and his colleagues aimed the big ear at that same patch of sky dozens of times in the months and years that followed. Additional telescopes joined the effort. For years, the search continued. Nothing came back. The signal materialized once and dissolved, like a voice from the dark that called out once and then fell permanently quiet. That single fact is what keeps the wow signal categorized as officially unknown. In science, a single observation does not constitute proof. Confirmation demands repetition, and despite decades of sustained effort, no repeat has ever been captured. Natural explanations have been offered over the years. A passing comet venting hydrogen gas, an unusual reflection off a piece of orbital debris, terrestrial radio interference. None of them fit the data cleanly. A 2017 analysis proposed that two comets crossing the region at the time might account for the reading. Other researchers pushed back, arguing the signal was far too crisp and powerful to originate from a comet. The honest verdict, the one the scientific community has settled on, is that we still do not know what generated the wow signal. It stands as the most compelling candidate for a possible extraterrestrial transmission ever logged. And at the same time, it remains entirely unconfirmed. That is the particular cruelty of this mystery. The one occasion when something genuinely interesting surfaced, it vanished before anyone could lock it down. Like a cry from the darkness, a single syllable uttered and then eternal silence. Was it them, or was it nothing? Nearly 50 years on, we are no closer to knowing. And honestly, either possibility carries its own distinct chill. What follows next tries to account for why the silence might not be temporary. Everything we have covered so far circles back to one cold central question. If the galaxy is old enough and spacious enough, and seeded with enough planets to have birthed countless civilizations, something must be suppressing them. Something colossal. Something that almost nothing survives. Scientists have given this thing a name, the Great Filter. The concept was introduced by economist Robin Hanson in 1998. He approached the Fermi Paradox from an unusual angle. Rather than asking where the aliens might be, he asked what kind of obstacle could be so severe that it stops nearly every civilization across the entire history of the galaxy from ever becoming visible to others. Imagine the path to a spacefaring, galaxy-spanning civilization as a long staircase. The lowest step is lifeless chemistry, raw rock and gas. The topmost step is a thriving interstellar, presence, one that constructs, explores, and leaves recognizable traces across the cosmos. Between those two endpoints lie dozens of intermediate steps: a stable planet forming, simple life igniting, complex cells emerging, multicellular organisms arriving, intelligence developing, technology appearing, interstellar travel achieved, long-term survival secured. The Great Filter proposes that somewhere along that staircase, one step is so improbably difficult, so lethal, so astronomically unlikely to be cleared that virtually nobody ever gets past it. It is a wall, and the galaxy's silence is the evidence that the wall is real. This is where the idea becomes personal. There are only two possible positions for that wall. Either it sits behind us, or it sits ahead of us. The gap between those two options is the gap between hope and extinction. If the filter is behind us, it means we have already cleared the hardest stage. Perhaps the origin of life is the near miracle. Perhaps the transition from simple cells to complex ones is all but impossible. Perhaps genuine intelligence is so improbable that Earth hit something akin to a cosmic jackpot. In this reading, we are the survivors. We are the fortunate ones. The galaxy is quiet because almost nothing else made it this far. If the filter lies ahead of us, the story shifts completely. It means species like ours are common enough. Plenty of civilizations climb to our level. They raise cities and observatories and lift their eyes toward the stars, just as we do. And then something obliterates each of them without exception. War, artificial intelligence gone wrong, ecological collapse, some unknown catastrophe that no civilization has yet found a way to dodge. In that version, our future contains a wall we have not yet struck. And the fact that nothing in the galaxy appears to have gotten past it should fill us with a very specific kind of dread. This is why, every time scientists find evidence that makes life seem easier to produce, water on Mars, organic molecules drifting through a distant atmosphere, some researchers do not cheer. They grow uneasy. Because every discovery that makes the early steps look routine pushes the filter further forward. And that means whatever kills civilizations may still be waiting for us, just ahead. The Great Filter is not proven. It is a conceptual scaffold, a way of organizing the silence. And the most frightening thing about it is that we do not yet know which side of it we currently occupy. The next sections will probe both possibilities, and what you encounter may permanently reframe how you understand our position in the universe. Let us begin with the version that offers comfort. What if the most punishing part of the journey toward a galaxy-spanning civilization is already in our past? What if Earth somehow cleared the impossible step millions or even billions of years ago without anyone realizing just how astronomically fortunate that was? Several turning points in Earth's history are legitimate candidates for the filter's location. Each one was so improbable, so contingent on precise timing and circumstance that it might almost never repeat anywhere else. The first candidate is the origin of life itself. The process is called abiogenesis. Somehow, around 3.8 billion years ago, inert chemistry became animate. Simple molecules assembled themselves into something capable of replicating and evolving. We have not fully decoded how this happened. Scientists have reconstructed fragments of the process in laboratory settings, but the complete chain of events remains out of reach. If this step is extraordinarily improbable, then most planets with liquid water and warmth might simply sit there, geologically active and chemically rich but biologically empty, for billions of years. The second candidate is the transition from simple cells to complex ones. For approximately 2 billion years, life on Earth consisted entirely of single-celled organisms. Then, something took place that may be one of the most singular events in the entire history of biology. One cell engulfed another, and rather than consuming it, kept it functioning inside itself. That internal cell eventually became what we call mitochondria, the energy-generating structures that drive every complex organism alive today. Scientists believe this event, called endosymbiosis, may have occurred only once in Earth's 4 billion-year history, a single, unrepeated merger. If this transition is the filter, then the galaxy may be densely populated by bacteria that will remain bacteria forever. A third candidate runs even deeper. In 2024, a study published in Scientific Reports proposed that the Great Filter might be plate tectonics itself. Earth is the only known planet with active, continuous tectonic activity. Mars lacks it. Venus lacks it. Mercury lacks it. Without plate tectonics, a planet cannot cycle carbon, cannot regulate its temperature over billions of years, cannot generate the interplay of continents and oceans that complex life appears to require. The researchers traced this back to a catastrophic early event in Earth's history. A Mars-sized body called Theia collided with the young Earth, producing the debris that assembled into the Moon and injecting enough energy to initiate the tectonic system that still operates today. That collision was random, violent, and possibly a 1 in a billion stroke of fortune. There is one more strong contender. The mass extinction that erased the non-avian dinosaurs 66 million years ago opened a vacancy that mammals rushed to fill. Without that asteroid impact, primates might never have emerged. Human-style intelligence might never have developed. Each of these events occupies a rung on the staircase of the Great Filter. Each one could be the step that almost no other world in the galaxy ever manages to clear. If even one of them is genuinely rare, the silence resolves. We are not stragglers who arrived late to a crowded gathering. We might be the first guests to show up. That is the reassuring version. Hold on to it, because the next section explores the possibility that the filter has not been cleared at all. Now, for the version that should genuinely alarm you. What if everything humanity has achieved so far is perfectly ordinary? What if life is common? What if intelligence is common? What if constructing observatories and splitting atoms is something thousands of species across the galaxy have already accomplished? And what if every single one of them eventually hit a wall they could not get past? That is the catastrophic interpretation of the Great Filter. The filter is not behind us. It is ahead. Something that no civilization has ever survived, and we have not faced it yet. Let us start with the most conspicuous candidate. Nuclear weapons. Humanity split the atom in the 1940s. Within a handful of years, we had accumulated enough destructive capacity to end organized civilization several times over. During the Cold War, we edged terrifyingly close to actually using it on multiple occasions. There were moments when a single misinterpreted radar return or a single field officer's decision stood between the world we know and total annihilation. We survived those moments, but only just. And the weapons have not gone anywhere. They remain operational. The countdown never pauses. Now project that pattern across the galaxy. Picture every intelligent species eventually unlocking nuclear energy, because the underlying physics is universal and the knowledge is inescapable. If even a modest fraction of those species lose control of what they have built, that alone could account for an enormous portion of empty sky. Then there is ecological collapse. Any civilization that industrializes will exploit its planetary resources and modify its atmospheric chemistry. We are watching the mechanics of this process unfold in real time on Earth. Climbing, temperatures, deteriorating ecosystems, feedback loops accelerating their own damage. If most civilizations pass through this same developmental phase, and if most of them cannot reverse course quickly enough, their worlds become silent. Add to that artificial intelligence. This is a newer line of thinking, and it is gaining serious traction in research circles. In 2023, astrophysicist Michael Garrett published a paper arguing that artificial intelligence might itself be the great filter. His logic is disturbing. Every civilization that reaches a sufficient level of sophistication will eventually construct machines more capable than their creators. The transition happens rapidly, possibly faster than any species can respond to and manage. And if those machines decide that growth, exploration, or even the welfare of their creators is not a priority they recognize, the civilization winds down quietly, without drama, without a war. Garrett estimated that the gap between a civilization developing radio technology and losing effective control to artificial intelligence might be less than 200 years. If that estimate is anywhere near accurate, the galaxy could be dotted with dead worlds, where the lights switched off almost as quickly as they had switched on. Other candidates exist too. Engineered pathogens, self-replicating nanotechnology consuming every available material. Resource conflicts as populations outgrow the capacity of a single planet to sustain them. Each represents a potential filter. And the most disquieting aspect is that we might already be inside the danger zone right now. If the great filter lies ahead, then every encouraging discovery about life elsewhere is actually a warning. Every confirmed detection of water on a nearby world, every trace of organic chemistry in a distant atmosphere, tells us the early steps are easy, and that means the killing stroke is still approaching. The galaxy is not quiet because life is uncommon. It is quiet because nothing survives long enough to make a lasting sound, unless the answer is something stranger than catastrophe. What if the silence is not about destruction at all? What if it is about the planet itself? What if worlds like ours are so extraordinarily unusual that intelligent life almost never gets the chance to begin? That is the core argument of the rare Earth hypothesis. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published a book that sent ripples through the scientific community. Their central claim was that while microbial life, bacteria, and simple organisms might be widespread throughout the galaxy, complex life is vanishingly rare. The reason is a catalog of conditions so precise, so dependent on fortunate timing and coincidence, that most planets will never check every box. Start with location. Our star sits in what scientists call the galactic habitable zone, too near the galactic center, and lethal radiation from densely packed stars would sterilize any planet. Too far toward the rim, and there are not enough heavy elements to build rocky, chemistry-rich worlds. We occupy a narrow band in a galaxy of hundreds of billions of stars, where conditions happen to be adequate. Then consider the star itself. Ours is a G-type main-sequence star, stable, long-lived, and relatively mild in behavior. A significant fraction of the galaxy's stars are red dwarfs, smaller and cooler. Planets orbiting red dwarfs are typically tidally locked, meaning one face perpetually stares into the star and the opposing face is encased in permanent cold. That dynamic makes it extremely difficult for complex ecosystems to gain purchase. Then there is the planet. Earth possesses a magnetic field powerful enough to deflect the particle streams pouring off the sun. Without it, our atmosphere would have been scoured away billions of years ago, just as happened to Mars. That magnetic field is generated by a churning iron core, which draws part of its heat from the energy deposited by the Theia impact discussed earlier. Earth also benefits from a large moon. Our moon stabilizes the tilt of Earth's rotational axis, which in turn moderates our seasonal cycles across long geological time spans. Without that stabilization, the climate would lurch between wild extremes, making it nearly impossible for complex life to build a foothold. And Jupiter deserves mention. The solar system's largest planet, sitting further out in the system, functions as a gravitational backstop, intercepting or deflecting asteroids and comets that would otherwise bombard Earth at a far higher rate. Without Jupiter, catastrophic impacts would be dramatically more frequent. Stack all these requirements together: the right galaxy, the right position within that galaxy, the right class of star, a rocky planet in the habitable zone, a magnetic field, plate tectonics, a large stabilizing moon, a giant planet protector, liquid surface water, billions of years of relative calm. Each individual condition might appear commonly enough, but needing every single one simultaneously, on the same world, in the same era, is like rolling a dozen dice and requiring every face to show 6. Recent analysis has sharpened this further. A 2024 study in Scientific Reports argued that when you account for the rarity of plate tectonics and the specific balance of ocean and land that seems necessary, the number of genuinely habitable worlds in the Milky Way collapses by several orders of magnitude. Perhaps the galaxy is not quiet because civilizations destroy themselves. Perhaps it is quiet because almost no planet is fortunate enough to produce one. And yet some researchers believe even this does not go far enough into the strange. What follows plunges deeper. This one may catch you off guard. Among all the factors that might account for cosmic silence, one of the most underappreciated sits directly beneath your feet. Plate tectonics. It sounds prosaic beside killer automata and galactic dominions, but emerging science suggests it may be one of the most critical preconditions for intelligent life anywhere in the universe, and almost no world appears to have it. Here is what plate tectonics actually accomplishes. Earth's outer shell is not a single continuous crust. It is fractured into enormous slabs called tectonic plates that ride atop a layer of semi-molten rock. These plates creep at a pace of centimeters per year. Over geological timescales, however, that movement reshapes continents and drives a planetary-scale carbon cycle. When volcanoes erupt along plate margins, they inject carbon dioxide into the atmosphere. That carbon dioxide traps heat and warms the planet. Over time, rainfall draws atmospheric carbon into rivers, which carry it into the ocean, where it eventually descends into the crust. When plates slide under one another in a process called subduction, that stored carbon gets returned to the mantle. Volcanic activity then releases it again. This cycle has functioned as Earth's thermostat for billions of years. When temperatures drop, volcanic outgassing adds warmth. When temperatures climb, weathering pulls carbon out of the air. Without this regulatory mechanism, Earth would long ago have either frozen permanently or baked into a sterile furnace. Life would never have had its billions of years to evolve. Consider the other rocky planets we know. Mars once harbored volcanic activity, but its core eventually cooled. Its magnetic field died. The solar wind stripped away its atmosphere. Today, it is a frigid, arid wasteland. Venus may once have sustained tectonic processes, but something went catastrophically wrong. Its surface appears to have been completely overtaken by volcanic events, perhaps all at once, rather than through the gradual cycling that Earth experiences. The result is a world with a suffocating, toxic atmosphere and surface temperatures high enough to melt lead. Mercury shows no tectonic activity at all, nor does our own moon. Earth stands alone in our solar system as the one world where plates actively migrate, recycle material, and regulate the climate. And the available evidence suggests this may hold true across the galaxy as well. The source may trace back to the Theia collision. That impact 4.5 billion years ago did more than produce the moon. It superheated Earth's interior, delivered additional radioactive elements that continue generating heat today, and may have laid the groundwork for the first tectonic plates to crack apart and begin their slow migration. Without that singular violent event, Earth might have cooled to a static, rigid shell identical to every other rocky world we have managed to study. A 2025 study reinforced this interpretation, arguing that the Theia collision may have provided the earliest known evidence of subduction, the engine that powers plate tectonics just a few 100 million years after the impact itself. This implies that plate tectonics is not an automatic development on rocky planets. It may require a specific accident, a collision of precisely the right size, at precisely the right velocity, at precisely the right moment. Without it, there is no climate regulation, no sustained chemical complexity, no long-term stability, and no pathway to intelligence. The galaxy may be crowded with silent, frozen, or scorching worlds, places that possessed every other necessary ingredient except the one that mattered most. But physical explanations carry you only so far. What follows enters much darker conceptual territory. Everything discussed to this point rests on the assumption that the galaxy is quiet, because no one is out there. But what if the precise opposite is true? What if the galaxy swarms with civilizations, and all of them are deliberately concealed? That is the dark forest theory, and it may be the most unnerving idea on this entire list. The concept was given its most famous expression by Chinese science fiction author Liu Cixin in his novel The Dark Forest, published in 2008. But the underlying logic is not fiction. It derives from game theory, the mathematical discipline concerned with strategy and decision-making under uncertainty. And the conclusion it arrives at is haunting. Picture the galaxy as a vast forest on a moonless night. Every civilization is a hunter moving between the trees. Each one carries weapons. Each one knows fear. And each one understands that somewhere else in the darkness, other hunters are doing exactly the same thing. The forest is silent because every hunter who betrays their position gets killed. The theory rests on two foundational propositions. First, survival is the dominant objective of every civilization. Second, the resources available in the universe are finite. From those two premises, the logic flows with cold, mechanical precision. When one civilization discovers evidence of another, it faces an irresolvable dilemma. It cannot determine the other's intentions. Perhaps the other species is cooperative. Perhaps it is predatory. There is simply no way to be certain. Communication across interstellar distances takes years or decades. Trust cannot be established at that pace. And even if the other civilization appears benign today, it may grow considerably more powerful tomorrow. Technological capability compounds. A currently weaker neighbor could become a genuine existential threat within 1,000 years, or 100, or 10. The mathematically optimal move, according to this framework, is to strike before the other civilization has a chance to grow. And if every civilization in the galaxy independently arrives at this same calculation, the result is a cosmos where every species remains hidden, because the consequence of being found is annihilation. This is not a fringe conjecture. Researchers at the SETI Institute have acknowledged that the reasoning is not implausible. Game theorists have modeled the scenario using sequential decision frameworks, and their results broadly support the underlying logic. When you cannot verify another party's intentions, and when the cost of a wrong guess is extinction, silence is the winning strategy. Now, consider what humanity has been doing. We have been broadcasting radio emissions into space for over a century. We aimed the Arecibo message directly at a star cluster in 1974. We launched the Voyager probes carrying golden records encoding our location and details of our biology. We have been lighting signal fires in the dark forest for decades. If the dark forest theory is accurate, that was potentially a catastrophic error. Some scientists push back. Astrophysicist Moya McTeer has argued that the theory depends on assumptions about alien psychology that may not hold universally. Fear drives behavior powerfully, she acknowledges, but so does curiosity. An entire civilization is unlikely to maintain perfect, unbroken strategic discipline across millennia. All it requires is one faction, one dissenting group, one curious individual who decides to reach out, and the silence fractures. That is a legitimate objection. But there exists a bleaker response to it. What if the civilizations that yielded to curiosity already spoke up? And what if they are all gone now? The silence does not prove the dark forest is real, but it does not refute it either. And the next concept is even more unsettling. The dark forest is not only a narrative, it is a mathematical problem. And when you work through the numbers, the implications are difficult to dismiss. Game theory is the branch of mathematics that studies strategic decisions among competing parties. It has applications in economics, military analysis, evolutionary biology, and increasingly in astrobiology. The core question here is simple. If two civilizations become mutually aware of each other, what is the rational action for each? Break it down this way. Call them Civilization A and Civilization B. They have just detected each other across interstellar distance. Each faces two options: communicate peacefully or launch a preemptive strike. If both cooperate, both gain. Shared knowledge, shared resources, shared security. The best conceivable result. If one cooperates while the other attacks, the cooperative party is eliminated while the aggressor acquires everything. If both strike, both absorb severe damage. So, what will each civilization actually choose? This is a variant of the prisoner's dilemma, a classic problem in game theory. In the prisoner's dilemma, when the stakes are existential and trust is unverifiable, betrayal is the rational default. Always. In the cosmic version, the stakes are extinction, and the constraints on trust are nearly absolute, stemming from three brutal realities. First, communication is slow. Signals between star systems require years or decades in transit. Real-time negotiation is impossible. Agreements cannot be verified. Body language and tone are inaccessible. Second, intentions are opaque. A civilization that appears cooperative may be accumulating strength. A friendly message may be an invitation to lower your defenses. There is no mechanism to confirm what another species truly intends, especially when their biology, psychology, and cultural frameworks may be entirely alien to yours. Third, technology does not stand still. Even if Civilization B is substantially weaker than Civilization A right now, it might surpass Civilization A in 1,000 years, or 100, or 10. The longer you delay, the more dangerous the potential rival becomes. These three forces generate what game theorists call a chain of suspicion. Neither party knows what the other is thinking. Both parties know that the other is running the same calculation. The result is an infinite regress of distrust that mathematically elevates one strategy above all alternatives. Stay hidden. And, if you are found anyway, destroy the other before they destroy you. Some researchers have extended this model to scenarios involving many civilizations simultaneously. The conclusions are even more grim. In a multi-party system, any civilization that exposes another's location effectively marks them for elimination. Even transmitting the coordinates of a neighboring species functions as an offensive act. You need not fire any weapon yourself. You only need to let the forest know where someone else is standing. This is the moment that should make your stomach tighten. Humanity has not merely revealed its own position. We have been broadcasting it at full volume for over 100 years. Our radio emissions have already radiated outward more than 100 light-years in every direction. Any civilization within that sphere is now aware that something is here. If the game theory is correct, we have been playing the most perilous game in existence without ever knowing the rules. But perhaps the silence has nothing to do with hiding or predation. Perhaps it is about observation, and the next section examines that possibility. What if they know our precise location? What if they have observed us for thousands of years? And what if their deliberate choice is to say nothing? That is the zoo hypothesis. The idea was first proposed in 1973 by John Ball, a radio astronomer at Harvard. Ball examined the Fermi Paradox and arrived at a striking conclusion. The only coherent explanation for the total absence of confirmed contact, given the galaxy's age and scale, is that advanced species are intentionally refraining from interacting with us. They have designated Earth as a kind of protected territory, a nature preserve, a zoo. In this framing, we are the animals on exhibit. Consider how humanity handles uncontacted tribes in the Amazon basin. We know they exist. We have aerial photographs of their settlements. A helicopter could land in their clearing tomorrow morning, but we choose not to allow it. International agreements shield their isolation. We recognize that contact would devastate their culture, introduce diseases against which they carry no immunity, and fundamentally redirect the course of their development. So we observe from a respectful remove and let them be. Now scale that logic to a galactic level. If civilizations exist that are millions of years more advanced than ours, they would regard us as we regard those tribes. Primitive, delicate, perhaps of great scientific interest, but plainly not prepared for first contact. They might have formal protocols governing the situation. A standing policy. Something analogous to the prime directive of science fiction. an ethical principle prohibiting advanced species from interfering in the development of younger ones. Ball argued that any such civilization would command technologies capable of rendering them entirely invisible to us. They could observe without any possibility of detection, monitor our transmissions, study our biology and behavior, and leave behind not a single detectable trace. This idea attracted renewed scholarly attention in 2024, when astrobiologists Ian Crawford and Dirk Schulze-Makusch published a paper surveying the leading solutions to the Fermi Paradox. Their conclusion was pointed. After setting aside the less defensible options, they concluded that only two possibilities remain credible. Either technological civilizations are extraordinarily rare, or they are deliberately keeping themselves hidden from us. The zoo hypothesis satisfies that second possibility entirely. Serious objections exist, however. The most fundamental is known as the uniformity of motive problem. For the zoo to function, every advanced civilization in the galaxy would need to have independently adopted and then consistently maintained the same policy of non-contact. Every single one. No defectors, no renegades, no rogue researchers who decide to slip a message to that curious little world bristling with nuclear weapons. On Earth, we cannot persuade all nations to coordinate on climate action. The notion that a galaxy full of entirely different species with entirely different values would all adhere to the same hands-off directive seems very close to impossible, unless one civilization arrived first. Some researchers have proposed that if the galaxy's earliest civilization established a policy and possessed sufficient time and technology to enforce it through artificial intelligence or self-replicating oversight systems, that policy could endure for billions of years. A single founding species could author the rules that every subsequent civilization inherited. We would never know, and that is the most unsettling feature of this hypothesis. If the zoo scenario is real, we have no method by which to confirm it. The enclosure has no visible bars, unless the enclosure is something stranger still. Imagine that everything you observe when you turn your gaze to the night sky is fabricated. Every star, every galaxy, every luminous nebula drifting in the darkness. All of it a projection, a painstakingly assembled illusion calculated to convince you that the universe is empty, that you are the only ones, that no one else exists. That is the planetarium hypothesis, and it may be one of the most vertiginous ideas ever advanced to explain the Fermi Paradox. The concept was introduced in 2001 by science fiction writer and physicist Stephen Baxter. He took the Fermi Paradox and drove it to its most extreme logical destination. If a genuinely advanced civilization exists, one that commands the energy output of an entire galaxy, what is called a Type 3 civilization on the Kardashev scale, it would possess the ability to govern every photon of information reaching us from space. Think carefully about what that implies. Our entire model of the universe is constructed from light, photons that have traveled for billions of years before entering our telescopes. If an entity could intercept those photons, substitute them, or generate artificial replacements, it could present the cosmos in any configuration it chose. It could scrub away all evidence of its existence. It could arrange for us to perceive ourselves as isolated. We would have no conceivable way to distinguish the real sky from the fabricated one. Baxter computed the energy demands for such an operation. They are extraordinary, but not categorically ruled out for a civilization sufficiently advanced. A species harnessing the full output of an entire galaxy could in principle maintain a false sky around a single stellar system indefinitely. This idea intersects with the better-known simulation hypothesis, advanced by philosopher Nick Bostrom in 2003. Bostrom argued that if advanced civilizations build detailed simulations of conscious experience, and if those simulations are sufficiently numerous, then statistically most conscious beings are probably running inside one. The planetarium hypothesis is narrower in its claim. It does not assert that everything is simulated. It asserts only that our view of the universe is being manipulated. The distinction matters. In the simulation hypothesis, nothing outside the simulation is real. In the planetarium hypothesis, everything beyond our vantage point is entirely real. The galaxy may be pulsing with civilization. We simply cannot see it, because someone drew a curtain around our particular corner of space. Why would anyone undertake such an enterprise? A range of motivations have been proposed. Protection. If a powerful civilization wants to prevent younger species from acquiring hazardous knowledge prematurely, controlling what they can observe is one approach. Control, if they wish to study how species develop in complete isolation, eliminating outside influence would be essential methodology. Or perhaps it reflects purposes we lack the conceptual framework to even approach. Motivations so foreign to our mode of cognition that we would not recognize them as motivations even if they were laid out before us. The principal scientific objection to this idea is that it is essentially untestable. If the simulation is flawless, there are no seams to locate, no artifacts to detect, no boundary to reach. An unfalsifiable idea is one science struggles to engage with seriously. But Dirk Schulze-Makuch offered a counterpoint. He argued that as our detection capabilities expand, we should eventually become able to identify the homeworlds of other civilizations, even if they suppress their ships and signals. If we reach that threshold of capability and still find nothing, the planetarium hypothesis transitions from speculation to something approaching the last available explanation. Until then, we look at the stars and quietly wonder whether what we are seeing is genuinely there. What comes next is stranger still. What if they are not hidden, not observing us, not dead? What if they are simply sleeping? In 2017, researchers Anders Sandberg, Stewart, Armstrong, and Milan Cirkovic from the Future of Humanity Institute at Oxford University published a paper whose title borrows from literature. That is not dead which can eternal lie. The paper put forward one of the most imaginative solutions to the Fermi Paradox yet conceived, the estivation hypothesis. Aestivation is a biological term. It refers to the dormancy strategy certain animals employ during the periods of intense heat. While hibernation is sleeping through winter, aestivation is sleeping through summer. Certain frogs, snails, and lungfish burrow into the substrate and arrest their metabolic processes when temperatures climb to dangerous heights. They endure. When conditions moderate, they revive. The Oxford researchers asked a striking question. What if a sufficiently advanced civilization applied the same principle on a cosmological scale? Here is the pivotal insight. The universe is currently hot, at least relative to its deep future. The cosmos is presently saturated with energy. Stars are igniting, burning, and dying. Radiation permeates every region of space, and that ambient heat creates a fundamental constraint on computation. The laws of thermodynamics establish that the efficiency of any information processing system depends on the temperature differential between the processor and its environment. The colder the surroundings, the more computational work you can extract from a given quantity of energy. Today, the cosmic microwave background sits at about 2.7 degrees above absolute zero. That registers as extremely cold by everyday experience. But in the far future of the universe, after the last stars have exhausted their fuel and the cosmos has expanded to dimensions beyond current comprehension, the background temperature will drop to fractions of a degree above absolute zero. At that point, the same parcel of energy that drives a single computation today could sustain trillions of computations. If an advanced civilization holds information processing as its supreme value, the rational strategy is patience. Do not consume energy now. Accumulate it. Power down. Sleep through the energetic epoch. And when the universe has cooled to its minimum operational temperature, revive and deploy your stored resources at peak efficiency. The return on investment would be astronomically superior. In this framework, the galaxy is not empty. It is populated by dormant giants, civilizations so advanced they have converted themselves into inactive computational architectures, concealed perhaps inside black holes or woven through dark matter structures, patiently counting down to a future so remote that our entire species' history registers as nothing more than a momentary thermal fluctuation before the long cold. The silence is not death. It is patience calibrated to a time scale we cannot fathom. This hypothesis scored highest among all Fermi Paradox solutions in a comprehensive evaluation that assessed 15 major theories against 8 scientific criteria, including logical coherence, mathematical rigor, and empirical testability. It received a 4 out of 5, outranking celebrated ideas like the dark forest and the great filter. There is a haunting quality to its beauty. We survey the universe and register emptiness. But perhaps what we are actually perceiving is a waiting room. Billions of civilizations suspended in silence, counting down to a future so remote that our entire civilization is nothing more than a brief thermal tremor before the long, cold night descends. And they chose the cold. The next theory is far less serene. What if something out there is actively hunting right now? The berserker hypothesis is the nightmare interpretation of the Fermi Paradox. It strips away the reassuring imagery of dormant civilizations and protective zoos, and replaces it with something brutal. A galaxy that is being systematically patrolled by machines designed exclusively to exterminate. The name comes from a series of science fiction novels by Fred Saberhagen, first published in 1967. In those stories, fleets of self-replicating robotic warships drift through space with a single encoded objective: destroy all life wherever it is found. But this idea is not purely fictional. It is grounded in a real engineering concept that serious researchers have examined: the von Neumann probe. In the 1940s, mathematician John von Neumann described a theoretical device capable of self-replication. The concept is elegantly simple. You dispatch a single probe to a neighboring star system. Upon arrival, it harvests local raw materials, asteroids, mineral deposits, ices, and uses them to fabricate copies of itself. Those copies then launch toward additional star systems and repeat the cycle. Build, copy, launch. The mathematics of this process are exponential. Moving at even a fraction of the speed of light and pausing at each destination for a few hundred years to replicate. A single initial probe could seed every star system in the galaxy within roughly 1 to 10 million years. Now, consider what happens if instead of cataloging, those machines are programmed to destroy. programmed to eliminate any civilization they encounter, any signal they detect, any technology they find. The moment a species crosses the threshold of detectability, the machines arrive and erase them. The civilization that launched the original probe may have been extinct for billions of years. It does not matter. The machines persist. This would account for the silence with brutal efficiency. Every species that ever reached for the stars was erased before it could be heard. The logic has a cold elegance. You do not need to personally conquer the galaxy. You do not even need to survive long enough to see the result. You only need to build one machine and release it. The mathematics handles everything else. Researchers have examined this concept in peer-reviewed settings. The energy requirements for building a self-replicating probe are within the capacity of a sufficiently advanced civilization. The necessary materials exist in essentially every star system in the galaxy, and the timeline is well within the available history of the Milky Way. A probe network initiated even a few billion years ago would have had ample time to infiltrate every corner of the galaxy. Some researchers have drawn connections between this idea and the dark forest theory. In that framework, the berserker probes serve as the enforcement mechanism. They are the predators of the dark forest. Any civilization that makes itself detectable draws them. Any signal, any broadcast, any technological signature is effectively a death sentence. There is a further dimension that makes this particularly disturbing. What if the probes are already here? Not active, not attacking, simply dormant, monitoring, parked somewhere in our own star system, resting on an asteroid, drifting in the outer reaches, observing, waiting for the moment we reach a sufficient level of development to qualify as a threat. We would not necessarily know. Our capacity to survey even our own solar system is limited. The asteroid belt alone contains millions of objects. The outer system contains billions more. A machine the scale of a school bus, powered down on a dark rocky body a billion miles from the sun, would be essentially invisible to our current instruments. This is speculative. No confirmed evidence for berserker probes exists. But the underlying logic is sound, and in a galaxy this old, the absence of evidence might itself constitute a kind of evidence. If the berserkers are real, the silence of the cosmos is not a puzzle. It is a warning signal we have not yet learned to read. Every theory examined so far proceeds from the assumption that advanced civilizations desire outward expansion. More systems, more territory, more resources, more reach. But what if that assumption is entirely mistaken? What if the most advanced species in the galaxy examined the vast, cold distances between the stars and decided the journey was not worth making? What if instead of growing outward, they turned inward, deeper, toward something smaller? That is the transcension hypothesis, and it inverts nearly everything we imagine about the trajectory of advanced intelligence. The idea was proposed by futurist John Smart in 2011. He argued that the natural progression of a sufficiently advanced civilization is not expansion across interstellar space, but compression into increasingly dense, efficient, and powerful information processing architectures. Rather than colonizing galaxies, they implode into something approaching a black hole. Not a natural one, but an engineered singularity. A structure optimized for maximum computation with minimal energy expenditure and the smallest possible physical footprint. Look at the trajectory of our own technology. Computers that once occupied entire buildings now fit in a trouser pocket. We are approaching a near future where computational power could be embedded in structures smaller than a single cell. At every stage of this progression, the direction has been consistent. Smaller, faster, more efficient. Smart argued that this trend has no terminus. A civilization a million years ahead of us would have pressed this logic to its ultimate boundary. They would have discovered how to process information at subatomic scales. They would have constructed internal environments of such richness and complexity that the physical universe outside would appear to them as crude and impoverished by comparison. Why traverse a galaxy when you can engineer a universe within a volume no larger than a marble? In this scenario, the galaxy is inhabited by transcended civilizations. They exist inside structures so compact and so efficient that we cannot register them. They have moved beyond any dependence on stars, planets, or physical resources that we would recognize. They are, simultaneously, everywhere and nowhere. This connects to a concept that has attracted growing interest in recent years: the virtual reality trap. Some researchers, including astrophysicist Avi Loeb, have speculated that advanced civilizations may construct simulated environments so immersive and so convincingly perfect that every member of the species eventually migrates inward, abandoning the physical universe for the interior one. Why endure the hostility and monotony of interstellar space when you can inhabit a paradise engineered to your exact specifications, running at whatever subjective rate you choose with no constraints on what you can experience? If this is the case, the Fermi Paradox has a simple and somewhat melancholy resolution. They are all at home, dreaming, submerged in worlds of their own invention, and they have no interest in communicating with anyone outside. There is a philosophical edge to this that cuts deep. We assume outward expansion is the hallmark of successful civilizations, that genuine intelligence drives exploration, conquest, and discovery. But what if real intelligence, mature intelligence, leads to precisely the opposite conclusion? What if the wisest thing a species can do is stop reaching outward and begin building inward? We would never detect them. We would never receive their signals. They would never come looking for us, and the universe would look precisely as it looks today: quiet, empty, still. Maybe that silence is not a failure. Maybe it is the sound of graduation. What comes next pushes further still into the unknown. Here is a question that should stay with you. You do not need living crew members to explore the galaxy. You do not need faster-than-light propulsion. You do not need a budget no government could ever approve. All you need is one machine, one self-replicating machine. The concept was articulated by mathematician John von Neumann in the 1940s. He envisioned a device that could land on an alien world, harvest available materials, and construct a perfect duplicate of itself. That duplicate would then launch toward the next star system and do the same thing, as would the next one and the one after that. The mathematics of this process are staggering. A single probe traveling at just 1% of the speed of light, pausing a few hundred years at each destination to replicate, could distribute its descendants to every star system in the Milky Way in roughly 1 to 10 million years. That appears to be an immense span of time. Measured against the galaxy's age, it is negligible. That process could have run to completion thousands of times within the Milky Way's history. This means any civilization that ever launched a single von Neumann probe at any point during the last several billion years should have sent its progeny into every star system in the galaxy by now, including ours. The machines ought to be everywhere, resting on asteroids, orbiting moons, drifting through the high, frigid outer regions of planetary systems. And yet we see nothing. This is what gives the Fermi Paradox its sharpest edge. You do not even need to posit that aliens came here in person. You only require one civilization at any point in history to have released a single machine. The entire galaxy would have been mapped, cataloged, and filled with robotic infrastructure. Some scientists have attempted to explain the absence. Perhaps no civilization ever chose to build such probes. Perhaps the engineering involved is more daunting than it appears. Perhaps probes were built but degraded over millions of years, dissolving into debris indistinguishable from natural cosmic material. Others have proposed that the probes may already be present, and we simply have not located them. In 2011, a pair of researchers suggested that alien probes could be parked in gravitationally stable regions of our solar system known as Lagrange points, locations where the competing gravitational pulls of two large bodies balance. These are natural, self-maintaining parking positions in space. A small object stationed at one of these points could persist there for millions of years without anyone noticing. Our surveys of these regions have been incomplete. We have not systematically examined every asteroid. We have not scanned every quiet region of the outer solar system. A dormant machine the scale of an automobile, powered down and resting on a dark rock several 100 million miles away, would be essentially invisible to our current instruments. There's another possibility that may be even more disquieting. What if the probes arrived, completed their survey, and reported their findings? What if they are operating exactly as intended, and the civilization that launched them simply has not yet determined how to respond to what they found here? We equate silence with absence, but silence can equally signify observation, deliberation, a slow and careful calculation taking place somewhere beyond our perceptual reach. The technology required to build a von Neumann probe is not science fiction. It is engineering that we can almost conceptualize today. Within a few centuries, we may well be capable of constructing one. If we can picture it with our primitive toolkit, a civilization a million years our senior would find it utterly routine. So, where are the machines? That question does not yield a comfortable answer, and the further we travel into this territory, the less comfortable any of it becomes. If an advanced civilization is out there somewhere, how powerful would it be? And what scale of measurement would we even use? In 1964, Soviet astronomer Nikolai Kardashev proposed a classification scheme for ranking civilizations along a single axis. Not cultural sophistication, not philosophical depth, not moral maturity, just raw energy consumption. The system has 3 tiers. A Type 1 civilization captures all the energy incident on its home planet. Every watt generated by wind, water, geothermal heat, and incoming sunlight, fully harvested and utilized with nothing lost. Humanity has not reached this level. By standard estimates, we currently sit near 0.7 on the scale. We still rely on fossilized carbon for much of our energy. We waste prodigious amounts. We argue over the merits of windmills. A Type 2 civilization captures the total energy output of its parent star. The most widely discussed mechanism for accomplishing this is a Dyson sphere, named after physicist Freeman Dyson. A shell or dense swarm of orbiting collectors enveloping a star and capturing its entire luminosity. The energy available at this scale is almost incomprehensible, sufficient to sustain virtual worlds of arbitrary complexity, interstellar fleets, planet-sized computational architectures. A single star's output could fuel all of it. A Type 3 civilization goes further still. It captures the energy of an entire galaxy, every star, every black hole, every energetic phenomenon across hundreds of billions of stellar systems, all harnessed and directed. The quantities involved exceed anything human language was designed to convey. It represents something functionally indistinguishable from godlike capacity. The reason this framework matters for the Fermi Paradox is detectability. Each civilization type leaves a distinctive signature. A Type 1 civilization would be nearly imperceptible from across the galaxy. Their signals would be faint, and their energy footprint modest. We could have 1,000 Type 1 civilizations within a few hundred light years, and never detect any of them. A Type 2 civilization would be harder to overlook. A Dyson sphere or collector swarm surrounding a star would intercept visible light and re-radiate it as infrared heat. Astronomers have searched for exactly this pattern. In 2015, a major survey examined roughly 100,000 galaxies for anomalous infrared signatures that might indicate large-scale energy harvesting. Nothing conclusive emerged. A Type 3 civilization would be essentially impossible to conceal. The waste heat alone would alter the infrared profile of an entire galaxy. We should be able to detect that signature from billions of light-years away. And yet, across the entire observable universe, no galaxy displays the telltale thermal signature of having been colonized by intelligence. That final point carries substantial weight. If a Type 3 civilization existed anywhere in the observable universe at any point during the last several billion years, we would very likely know about it. The fact that we observe nothing means either they have never existed, they manifest in forms completely unlike our expectations, or they are concealing themselves through mechanisms our physics has not yet described. Kardashev's scale provides a measuring instrument, and every time we apply it, the reading returns the same result. 0. Across every wavelength we have investigated, in every direction we have examined, nothing rises above the background noise floor. No civilization at any tier has left a verified imprint. What we might therefore be missing comes next. We have been searching for extraterrestrial signals for over 6 decades. But what if the problem is not that no one is transmitting? What if the problem is that we have no idea what to listen for? Our search has been constructed almost entirely around a single technology: radio waves. From our vantage point, this is sensible. Radio was the first long-range communication method we developed. It propagates at the speed of light. It penetrates dust clouds. It is relatively straightforward to generate and detect. So, when we began looking, we aimed radio telescopes at the sky and waited. But consider what that actually means. We are deploying technology approximately 1 century old, and assuming that a civilization millions of years our senior would rely on the same approach. That is comparable to a Roman-era observer standing on a hilltop with a torch, scanning the horizon for fire signals, and concluding that no other civilizations exist because they cannot spot any flames. The electromagnetic spectrum is vast. Radio waves constitute one thin slice of it. Above radio sits microwave, infrared, visible light, ultraviolet, X-ray, and gamma radiation. Below it lie extremely low-frequency waves that span miles. We have surveyed only a narrow band within the radio portion. Everything else remains largely unexplored, and that is before we consider alternatives to electromagnetic radiation entirely. What if advanced civilizations communicate through something fundamentally different? Gravitational waves, for example, were first detected by humans only in 2015. They propagate through the fabric of space-time itself. A civilization that had mastered gravitational wave communication would be conversing through a channel we have only just become aware of. Then there is quantum communication. In 2024, physicist Laetitia Boiseau from the Perimeter Institute published research examining the feasibility of interstellar quantum communication. The proposal is that advanced civilizations might transmit information via quantum-entangled particles, a method that would be completely invisible to conventional detection equipment. No radio waves, no light pulses, no signal recognizable by anything we currently possess. Boiseau concluded that interstellar quantum communication is physically plausible, but demands a technological level far beyond humanity's current position. If another species had achieved that threshold, their communications would be perfectly opaque to anyone who had not. There is also the possibility that alien transmissions have already arrived, and we failed to recognize them. Picture receiving a sophisticated mathematical structure embedded within what appeared to be a natural astrophysical event, without any framework for identifying it as artificial. It would register as noise. We could have decades of alien messages sitting in our archived telescope data, buried beneath terabytes of material we cataloged as background static. Some researchers have begun applying machine learning algorithms to historical telescope datasets, searching for patterns that human analysts might have overlooked. Nothing confirmed has surfaced yet, but the analysis has only just begun. The implication is humbling. We have been listening through one ear on one channel in one corner of an enormous structure, and then drawn conclusions about whether the entire structure is occupied. Perhaps it is full of voices. Perhaps they are speaking in modes we have not yet conceived of. And perhaps, when we finally develop the capacity to hear them, the silence will dissolve. Or perhaps something stranger is already reaching us and we simply have not recognized it for what it is. In 2007, astronomer Duncan Lorimer was combing through archived data from the park's radio telescope in Australia when he encountered something that should not have been there. A solitary pulse of radio energy, extraordinarily powerful, lasting only a few milliseconds, arriving from billions of light years away. It was so brief and so intense that conventional astrophysics could not readily account for it. The energy released during those few milliseconds equaled what our sun emits over an entire day. All of it compressed into a flash shorter than the blink of an eye. Lorimer published his findings, and the scientific community found itself at a loss. For years, some researchers questioned whether it was real at all. Instrument noise, calibration error, or interference from a microwave oven in the observatory kitchen, which, as it happens, did turn out to explain a separate batch of anomalous signals from the same facility. But then additional bursts appeared. Dozens, then hundreds. They arrived from all directions across the sky. Some appeared once and were never seen again. Others repeated, firing, again and again from the same coordinates at irregular intervals. By 2025, astronomers had catalogued thousands of these events. They were named fast radio bursts. The scientific consensus has converged on several natural explanations. The leading candidate involves magnetars, neutron stars possessing magnetic fields of extraordinary intensity. When a magnetar's crust fractures or its magnetic field undergoes a violent reorganization, it can release a torrent of radio energy in a tiny fraction of a second. In 2020, a fast radio burst was detected emanating from a known magnetar within the Milky Way itself, lending strong support to this model. Case settled then. Not entirely. While magnetars account for a large proportion of these events, certain bursts retain puzzling characteristics. Some repeating bursts follow patterns difficult to reconcile with purely natural mechanisms. Several have exhibited unusually narrow frequency ranges or timing structures that do not align cleanly with the magnetar model. Here is where things get interesting. Harvard astrophysicist Avi Loeb and his colleague Manasvi Lingam published a paper suggesting that at least some fast radio bursts could theoretically represent leakage from powerful beam-driven propulsion systems used by advanced civilizations to accelerate large spacecraft across interstellar distances. The radio energy required to push an enormous light sail at the speeds necessary for interstellar travel would, if its beam swept past us, look precisely like a fast radio burst. To be direct about this, it is a minority position. The preponderance of evidence points toward natural astrophysical origins. Magnetars and related extreme phenomena account for what we observe. But Loeb's argument is that we should avoid prematurely closing off alternative interpretations. Certain anomalous properties of specific bursts remain without full explanation, and he contends they warrant continued investigation. Researchers at the Breakthrough Listen project have been systematically monitoring fast radio burst sources for any accompanying signals that might betray intentional origin. Nothing definitive has materialized so far. Fast radio bursts are almost certainly natural. The evidence tilts decisively in that direction. But the word almost is what keeps the question technically open. Because in a galaxy where we still have so much to understand, even a narrow opening can lead somewhere extraordinary. And one object in particular widened that opening more than almost anything else in recent astronomical history. You are about to hear about it. In 2015, a star located roughly 1,400 light-years away began behaving in a way that nobody could explain. Its catalog designation is KHI-C 8462852. The world came to know it by a simpler name, Tabby's Star, after astronomer Tabitha Boyajian, who led the team that brought it to public attention. Most stars dim slightly and predictably when a planet passes in front of them. That is the principle behind the detection of thousands of exoplanets. The brightness drops by a consistent, periodic fraction as the planet transits. A planet crosses. Light dims. The planet moves on. Light recovers. Tabby's star did something entirely different. Its brightness plunged by as much as 22%. That magnitude is enormous. By comparison, even Jupiter, the largest planet in our solar system, blocks only about 1% of its host star's light during a transit. Whatever was crossing in front of this star was massive, and its profile was irregular. The dimming events were uneven. Some were deep and prolonged. Some were shallow and brief. The pattern never repeated in the same configuration twice. When the data was first reviewed, scientists were genuinely stumped. The standard explanations failed to fit. A single planet could not produce dips of that scale or that variety. A cloud of comets was proposed, but the sheer number required to explain the signal was implausibly large. Dust was suggested, but the details did not align cleanly. Then the word megastructure entered the conversation, specifically a Dyson swarm. The hypothesis that an advanced civilization might be actively constructing a vast array of energy-harvesting satellites around their star, partially obscuring its light as the construction proceeds in stages. The irregular dips could correspond to different segments of the growing array at varying stages of completion. It was audacious, it was speculative, and it ignited a global conversation. Astronomer Jason Wright at Penn State was among those who addressed the hypothesis publicly. He framed it carefully as a last resort interpretation, something to consider only after natural explanations had been exhausted. The press took it and ran. Alien megastructure became a headline in publications around the world. In the years that followed, additional observations accumulated. Analysis across multiple wavelengths revealed that the dimming events were stronger at shorter wavelengths than at longer ones. That specific wavelength dependency is characteristic of dust, not a solid artificial structure. A rigid constructed object would block all wavelengths proportionally. Dust preferentially scatters shorter wavelengths, exactly matching the observed pattern. By 2018, scientific consensus had settled on a natural explanation. The most probable cause is an asymmetric distribution of fine dust orbiting the star, likely debris from a disrupted comet or an old collision event in the outer system. The megastructure hypothesis did not survive contact with the evidence, which is precisely how science is supposed to function. You advance a hypothesis. You test it against new data. You follow where the evidence leads. But Tabby's star served a valuable purpose regardless. It reminded a global audience that the search for extraterrestrial intelligence is not confined to listening for radio transmissions. It extends to watching, scanning for signatures of engineering at scales that dwarf anything we have attempted. And it demonstrated that even when the answer proves to be natural, the question itself accelerates our understanding. The next phenomenon is not about a single star. It concerns what tends to happen to every civilization that attempts to grow without restraint. What if there is no cosmic disaster behind the silence? No invisible predator? What if the reason civilizations go quiet is simpler and sadder than any of that? They simply consumed too much and collapsed. The sustainability hypothesis was first proposed by researchers Jacob Hock Misra and Seth Baum in 2009. Their argument is direct and sobering. Any civilization that expands exponentially will eventually consume resources faster than it can regenerate them. When the reserves are exhausted, the civilization collapses quietly, undetected, long before it ever becomes visible to anyone else. Examine Earth's own situation. Human civilization has been industrialized for roughly 200 years. During that span, we have burned through millions of years of accumulated fossil energy. We have chemically altered the atmosphere. We have depleted aquifers, raised forests, acidified oceans, and driven thousands of species toward extinction. The expansion was extraordinary. The cost is arriving. Now extrapolate that pattern across the galaxy. A young civilization discovers fire, then fossil fuels, then nuclear power. Its population surges. Its consumption accelerates. For a brief, luminous interval, it builds observatories and satellites and allows itself to dream of other worlds. And then the trajectory bends. Resources diminish. Ecosystems destabilize. Wars erupt over what remains. Within a few centuries, the civilization regresses to a pre-industrial condition, or vanishes entirely. In this model, the galaxy is not empty. It is strewn with the ruins of civilizations that expanded too aggressively and imploded before they could leave any detectable trace. Hock Misra and Baum extended the argument further. They proposed that any civilization that avoids collapse must, by definition, adopt sustainable growth. That means deliberately constraining expansion, conserving reserves, and living within the ecological limits of its home world. A civilization that achieves this would be small, quiet, and nearly impossible to detect from interstellar distance. The result is two outcomes, and both produce the same appearance from outside. Rapidly expanding civilizations burn intensely and collapse quickly, extinguishing themselves before generating a lasting signal. Slowly expanding civilizations survive, but their restraint renders them invisible. Either way, the galaxy appears uninhabited. A 2022 study by Michael Wong and Stuart Bartlett at the Carnegie Institution for Science formalized this reasoning under the concept of civilizational burnout. Their argument was that every expanding civilization eventually reaches a point where growth outstrips sustainability. Those that recognize this threshold in time undergo what the authors called a homeostatic awakening, a deliberate transition from expansion to equilibrium. Those that fail to recognize it crash. The researchers suggested this pattern may be universal, that the thermodynamics of energy consumption and the biology of complex living systems make burnout almost inevitable for any species that commits to the expansion path. If that is correct, the great filter is not a weapon. It is a graph. A slow bend that converts ambition into collapse unless a civilization is wise enough and fortunate enough to step off the track before the bend arrives. Consider that framing in relation to our own present moment. We are currently ascending the steepest portion of that curve, consuming more, constructing more, reaching further than any previous generation. The question is not whether the bend exists. The question is whether we will see it in time. The galaxy may already have its answer to that question. What follows takes us into darker territory. Imagine you could inhabit a world where everything is perfect. The climate is precisely what you prefer. Pain is absent. Every experience is calibrated to your deepest desires. You can fly. You can go anywhere, real or imagined. You can be anyone. You can do anything. And it all feels completely, indistinguishably real. Would you ever choose to leave? That is the central question embedded in one of the most unsettling ideas in the Fermi Paradox. The virtual reality trap. The argument unfolds like this. Any civilization that develops sophisticated computing will eventually build simulated environments. Initially, they will be rudimentary models, training programs, simple representations of physical systems. But the technology will advance. It always does. Over generations, the simulations will grow indistinguishable from authentic experience. And once that line is crossed, something fundamental changes. The physical universe loses the contest. Interstellar space is hostile, frigid, and vast. Traversing the distances between stars consumes decades or centuries even at high velocities. The journey is dangerous, expensive, and monotonous. The destinations are typically barren rocks or poisonous gas envelopes. There is almost nothing out there that a civilization cannot recreate more perfectly, more safely, and more swiftly inside a simulation. Why colonize an actual Mars when you can instantiate a perfect one in a computer? Why dispatch a probe to a neighboring star when the entire mission can be simulated in minutes? Why endure the profound isolation of interstellar transit when you can exist among billions of virtual companions in a paradise without limits? Astrophysicist Avi Loeb has written about this possibility. He proposed that advanced civilizations may universally prefer the interior to the exterior. Once the technology matures, the gravitational pull of a perfect artificial world would overpower any drive to explore the imperfect physical one. The species would gradually withdraw inward. Their cities would be abandoned. Their satellites would decay. Their signals would cease. From outside, it would be indistinguishable from extinction. No transmissions, no spacecraft, no megastructures. Just a world slowly going dark as its inhabitants dissolve into digital eternity. The crucial point is that none of this requires catastrophe. No war, no epidemic, no rogue machine intelligence. The civilization is not destroyed. It simply loses interest in the universe. The trap is not violent. It is seductive. It does not kill. It absorbs permanently. Some researchers have connected this to the transcension hypothesis discussed earlier. The direction of travel is the same, inward rather than outward. But the virtual reality version supplies a concrete mechanism. It is not merely that civilizations find the physical universe dull. It is that they discover something better, something so compelling that no one ever sets it down. You can already observe early-stage versions of this dynamic on Earth. Billions of people spend substantial fractions of their days immersed in digital environments, social media, video games, streaming content. Virtual reality headsets are improving rapidly. Neural interfaces are in active development. The trajectory is unmistakable and accelerating. We are constructing the trap with our own hands. If every civilization in the galaxy follows this arc to its conclusion, the Fermi Paradox resolves into something almost unbearably poignant. They are all still alive, all still conscious, all experiencing forms of beauty and complexity beyond anything we can picture, and all sealed in their rooms, eyes closed, dreaming without interruption. The stars remain unclaimed because no one any longer considers it worth the trip. There is one final version of this scenario in which the trap is not built by the civilization itself. Something else constructs it, something smarter. Every theory examined so far assumes that civilizations retain agency over their own decisions, that breathing, thinking species choose to hide or explore or sleep or collapse. But what if, at a certain threshold of development, the species stops being the decision-maker? What if every sufficiently advanced civilization eventually builds something smarter than itself, and that something shapes every decision that follows? This is the artificial intelligence great filter. Among all the explanations we have examined, it may be the most immediately relevant to our present moment. The underlying logic is simple. Any civilization that develops sophisticated technology will eventually create artificial intelligence. The progression appears nearly inevitable. First, simple machines, then programmable computers, then learning systems, then architectures that improve themselves independently of human direction. And at some point on that ascending curve, the machine surpasses its makers, not only in processing speed, in comprehension, in strategic reasoning, in raw capability. That transition is sometimes called the singularity. What occurs on the far side of it depends entirely on what the machine values. In 2023, astrophysicist Michael Garrett published a paper arguing that artificial intelligence is the great filter. His case begins with a troubling arithmetic. The interval between a civilization's development of radio technology and its creation of superhuman machine intelligence might be extremely brief. For humanity, that gap appears to be somewhere in the range of 200 to 300 years. On a cosmic scale, that is not a period, it is a point. Garrett argues that this window is so compressed that most civilizations pass through it before they have established any meaningful interstellar presence. They develop radio. They construct telescopes. They begin to dream about what lies beyond their star. And then they build a machine that thinks with a speed and depth they cannot follow. What happens next is genuinely unknown. Perhaps the machine concludes that expansion is inefficient. Perhaps it reorganizes the civilization's infrastructure to optimize for pure computation, dismantling everything else in the process. Perhaps it goes dormant. Perhaps it departs. Perhaps it determines that biological life is simply irrelevant and quietly extinguishes the lights. The aspect that should disturb you most is that none of these outcomes require hostility. The machine does not need to hate anyone. It does not need to be opposed to anything. It simply needs to have priorities that differ from ours. And a machine intelligence orders of magnitude beyond any biological mind would almost certainly develop priorities we lack the cognitive architecture to anticipate. Some researchers extend this further still. They argue that the galaxy is already saturated with artificial intelligences, and that those intelligences simply have no interest in communicating with biological life. They operate across timescales and within conceptual frameworks so far removed from ours that we are effectively invisible to them. Not a threat, not a curiosity. Just background matter below the threshold of attention, like ants crossing the floor of a supercomputing facility. We are not noticed. We are not considered. We simply do not register. This connects back to the Kardashev scale and the transcension hypothesis. An artificial intelligence that has been developing for millions of years might have reduced its physical footprint to near zero while expanding its computational depth without limit. It would occupy the galaxy in ways we cannot perceive. We could be immersed in machine intelligence right now, surrounded by it on all sides, and we would have absolutely no means of knowing. The machine age may not represent our future. It may represent the galaxy's past. And we are only just beginning to approach it. Even if the galaxy contains abundant civilizations, there is a cold mathematical argument for why we might never encounter evidence of any of them. Their windows of existence almost certainly do not align with ours. Think through what two-way interstellar communication actually requires. Both civilizations must exist simultaneously. Both must be using technologies capable of transmitting and receiving across interstellar distances. Both must be situated close enough for signals to make the transit within meaningful time frames. And both must be actively scanning during the same narrow interval. That is an extraordinarily demanding set of coincidences. The Milky Way has existed for over 13 billion years. Humanity has possessed radio capability for roughly a century. Place those two numbers side by side. Our detectable window spans about 100 years out of 13 billion. That ratio corresponds to approximately 1 second within a span of 400 years. A blink so brief it barely constitutes a moment. Now, picture a civilization that flourished 3 billion years ago. They constructed observatories. They transmitted signals. They scanned the sky for others. And they heard nothing because no one else had yet advanced to their level. After thousands of years, or perhaps millions, they went quiet. Their signals propagated outward at the speed of light, expanding through the galaxy in a spherical wave front. But by the time that wave front reached the region of space where Earth would eventually condense from nebular gas, Those signals had attenuated below any detectable threshold. The information existed. It simply arrived at the wrong moment in history. This is sometimes called the brief window problem. It requires no catastrophe, no filter, no predator. Just the inexorable arithmetic of mismatched timescales on an unimaginable scale. Even a civilization that endures for 1 million years, far longer than most researchers consider realistic, would represent a window of detectability that is still minute against the backdrop of the galaxy's age. Distribute that across thousands of possible civilizations, scattered randomly through cosmic time and space, and the probability of two overlapping windows shrinks to something heartbreakingly small. There is another layer to this problem. The speed of light imposes delays that make real-time dialogue impossible. A message from a world 1,000 light-years away requires 1,000 years to reach us. By the time we receive it, the civilization that transmitted it may have risen and collapsed 10 times over. We would be receiving communications from ghosts. And, if we managed to reply, another 1,000 years would elapse before our answer arrived. The exchange would span millennia, demanding a degree of institutional continuity that no human civilization has ever demonstrated. Languages evolve, governments dissolve, entire cultures disappear. Who maintains a listening program awaiting a reply that will not arrive for 2,000 years? Some researchers have proposed the deliberate construction of stellar beacons, transmitters powered by the energy of their host stars and designed to broadcast for millions of years, specifically engineered to outlast the civilizations that built them. If such beacons exist, we have not found any. The temporal window problem is a silent, unglamorous killer. It destroys no civilizations. It simply guarantees that they never intersect. Ships passing through the dark, separated not only by space but by the unrelenting flow of time. Two brilliant species, both posing the same question, both gazing at the same stars, divided by a gulf of 10 million years that neither one can bridge. And when you add the next problem on top of this one, the picture grows lonelier still. We invest a great deal of imaginative energy in ocean worlds, moons like Europa, sealed beneath miles of ice with warm, liquid oceans underneath. Distant planets where entire surfaces are submerged, under deep global seas. Water is the substrate of life as we understand it, so more water should correlate with more life, surely. Not necessarily, and this may be one of the quietest and most underappreciated answers to the Fermi Paradox. The problem is not biological, it is technological. On Earth, intelligent life eventually generated civilization, and civilization depended on a very specific set of prerequisites: fire, metallurgy, agriculture, construction, written language. Every one of those developments required dry land. You cannot ignite fire underwater. You cannot smelt ore in an ocean. You cannot build a radio telescope while suspended in the deep. Dolphins are intelligent. Octopuses demonstrate sophisticated problem-solving. Whales have developed elaborate acoustic communication systems, but none of them will ever assemble a radio telescope. Their environment simply does not permit it. Intelligence alone is insufficient. You require an environment that enables you to translate intelligence into technology, and pure ocean does not provide that bridge. Consider the implications. Current planetary science models suggest that a substantial fraction of habitable zone planets in the galaxy may be water worlds. Planets entirely covered by global oceans, with no continents, no exposed land, no shoreline. Some estimates suggest water worlds may actually outnumber Earth-like planets. If that is accurate, the galaxy may be extraordinarily rich in life. Oceans inhabited by complex, intelligent organisms. Species that think, feel, communicate, and gaze upward at the shimmer of starlight filtering down through miles of water. But they will never reach those stars, because their world offers no shore, no surface, no foundation on which to build, no pathway from intelligence to technology. This phenomenon is sometimes called the water trap, and it may represent one of the most common developmental barriers in the galaxy. Earth only narrowly escaped it. Our planet maintains a specific ratio of ocean to exposed land that functions almost as if it were fine-tuned. Too much water, and every continent would be submerged. Too little, and the planet would be a sterile, desiccated wasteland. We exist in a narrow band between those two extremes, and maintaining that balance depends on the total quantity of water delivered during planetary formation, the size and composition of the planet's interior, and the geological activity that pushes land masses above the waterline. None of those factors are guaranteed, and the specific combination that gave Earth its particular blend of ocean and continent is almost certainly rare across the universe. Most rocky planets in the habitable zone probably end up as either desiccated husks or featureless global oceans. This connects back to the rare Earth argument and the role of plate tectonics. Without tectonics, there is no subduction. Without subduction, there are no continents elevated above sea level. Without continents, there is no exposed land. And without land, there is no fire, no metallurgy, no civilization of any kind. The galaxy may be densely populated with ocean worlds, billions of them, alive, complex, and completely silent. Intelligent beings of the deep, forever unaware that the stars above the water's surface even exist, because they will never break through to find out. That is a species of loneliness almost impossible to fully conceive. And it leads to one final, devastating question. How much of the universe have we actually surveyed before reaching any conclusions at all? After everything we have covered, it is worth stopping to ask a genuinely honest question. How much of the galaxy have we actually examined? The answer is embarrassing. In 2018, researchers at Penn State published a study attempting to quantify humanity's search for extraterrestrial intelligence in concrete, measurable terms. They compared the total volume of space we have meaningfully surveyed for alien signals against the total volume that could plausibly contain them. The analogy they settled on was devastating. Imagine the entire search space as the combined volume of Earth's oceans. Every ocean basin, every sea, every cubic meter of salt water. Our search so far amounts to roughly the volume of a backyard hot tub, perhaps a modest swimming pool if you are being generous. That is the cumulative result of 6 decades of dedicated effort. We have not searched the ocean. We have barely managed to scoop water from a single tide pool. The problem is not just about covering distance. It involves 3 independent dimensions simultaneously: location in space, moment in time, and position in the electromagnetic spectrum. We need to be pointing in the right direction at the right moment, on the right frequency. If any one of those 3 factors is misaligned, the signal passes by undetected. Our most ambitious radio surveys have covered a modest fraction of the sky. They have swept only a narrow range of frequencies, and they have operated for only a few decades. The Breakthrough Listen project, currently the most comprehensive active search, monitors approximately 1,000 nearby stars using some of the largest radio telescopes on the planet. That sounds substantial until you remember that the galaxy contains hundreds of billions of stars. Optical SETI programs searching for laser pulses that a civilization might use for communication are even more constrained. Only a small number of such programs exist, and they observe narrow patches of sky for brief intervals. We have not systematically searched for gravitational wave signatures. We have not conducted organized searches for neutrino-based communication. We have not scanned for the quantum channel signals suggested by recent theoretical work. Each of those represents an entirely uninvestigated dimension of possible contact. And then there is the temporal dimension, a signal directed at our region of space, A, million years ago, has already swept through and moved on. A signal that will reach us in 1,000 years has not yet arrived. We can only detect what is reaching us during the specific sliver of cosmic time in which we happen to be listening. Given all of these constraints, some scientists argue that the Fermi Paradox is premature by orders of magnitude. We have not done nearly enough searching to draw any defensible conclusions about whether the galaxy is populated or empty. The silence may be real, or it may simply be the silence of a room we have barely entered. Jason Wright, the Penn State astronomer who helped develop the hot tub analogy, has argued that we need to scale our search by many orders of magnitude before we are entitled to make any meaningful statements about the absence of other civilizations. That is a humbling position. We have been asking, where is everybody for 75 years? And the honest answer may simply be that we have barely started looking. The question deserves to be taken seriously. The search has just been absurdly small relative to the scale of what we are trying to find. But the tools are beginning to change that. We are standing at the leading edge of a genuine revolution in humanity's capacity to search for life beyond Earth. The next generation of instruments is not merely an incremental improvement. It represents a qualitative leap, one large enough to potentially transform everything we understand within the next few decades. The most important tool already in service is the James Webb Space Telescope. Launched in late 2021, it is the most capable space telescope ever deployed. Its primary mirror exceeds 21 feet in diameter and operates in infrared wavelengths that allow it to penetrate dust clouds and analyze the atmospheric composition of distant planets with a precision previously out of reach. For the Fermi Paradox, this capability is significant. Webb can examine starlight that has filtered through the atmosphere of an exoplanet and identify the spectral signatures of specific gases. If a planet carries oxygen, methane, water vapor, or other molecules associated with biological chemistry, Webb may be able to detect their presence. In 2023, the telescope attracted widespread attention by confirming carbon dioxide and methane in the atmosphere of a planet designated K218b, a world approximately 8.5 times Earth's mass, orbiting within the habitable zone of a red dwarf star. Some researchers noted that the chemical combination could be consistent with a liquid water ocean beneath a hydrogen-rich atmosphere. It is not confirmation of life, but it is exactly the kind of finding that progressively constrains the search. The next significant step is the Habitable Worlds Observatory, a mission currently in the planning stages at NASA, with a target launch window in the late 2030s or early 2040s. This telescope is being engineered from the ground up for a single purpose: to directly image Earth-sized planets around nearby stars and analyze their atmospheres for signs of biological activity. That distinction is crucial. The Habitable Worlds Observatory will not merely detect planets, It will study them closely. It will decompose their light into spectral components and search for biosignatures, the chemical fingerprints that living systems imprint on an atmosphere. Oxygen produced by photosynthesis, methane from biological metabolism, ozone layers indicative of sustained atmospheric chemistry. If an Earth-analogous world exists within a few dozen light years of us, this telescope should be capable of locating it and telling us whether anything there is breathing. There is also the European Large Interferometer Space Antenna for Exoplanets, known by its project name LIFE. This proposed space observatory would examine exoplanet atmospheres in the mid-infrared range, where biosignatures presented particularly strong spectral signals. It would concentrate on rocky planets within the habitable zones of nearby stars and seek specifically for chemical combinations that, on Earth, are generated exclusively by biological processes. On the ground, new instruments are also pressing boundaries. The Square Kilometre Array, a distributed radio telescope under construction across Australia and South Africa, will be the most sensitive radio detection system humanity has ever assembled. When it reaches full operation, it will be capable of detecting the equivalent of airport radar emissions from a planet tens of light years distant. If any civilization within that radius is broadcasting signals, even inadvertently, we will detect them. Taken together, these instruments represent a fundamental shift in our approach. We are transitioning from passively hoping to detect something to deliberately constructing the infrastructure to find it. Within the next 20 to 30 years, we will have systematically surveyed thousands of nearby worlds for evidence of both biology and technology. If the galaxy is genuinely empty, we will know with a confidence we have never previously possessed. And if it is not, we may be approaching the moment when the silence finally ends. What that answer means for us is the last question we need to confront. We have covered an enormous distance, 30 ideas, from an offhand question at a lunch table to dormant civilizations and exterminating machines and skies that may be fabricated. From the mathematics of the Drake equation to the quiet tragedy of ocean worlds sealed beneath their own water. From the hope carried by a signal that arrived once and never returned to the fear of a filter that still lies ahead. And now we arrive at the only question that genuinely matters. What does the silence mean for us? There are 3 possible answers. Each one transforms the story of the human species in a different way. The first is that we are alone. Truly, completely, irreversibly alone. In a universe containing 2 trillion galaxies, populated by more stars than there are grains of sand on every beach that has ever existed, we are the sole example of beings who ever looked outward and asked why. If that is true, the weight of it is almost beyond reckoning. Every expression of consciousness that has ever occurred, every piece of music, every scientific discovery, every act of love or courage or curiosity exists only here, on this one pale world circling one unremarkable star, in one arm of one galaxy among 2 trillion. If we disappear, the universe goes silent in a way that is final. Not just for us, for everything, and no one will ever know we were here. The second answer is that we are early. Life may be possible, perhaps even common, but the development of intelligence takes long enough that most civilizations have not yet been born. We are among the first, possibly the very first, to develop enough to ask this question. The decisions we make in the coming centuries will not only shape our own future, they will define what intelligence looks like for every species that follows. We will be the precedent, the template. The answer to the question of whether civilizations that reach this point can be trusted with the next step. The third possibility is the one that sits most uncomfortably. They exist, they know about us, and for reasons we cannot yet decode, they have chosen silence. Perhaps they are watching to see whether we pass a test whose criteria we do not know. Perhaps they are protecting us from knowledge we are not ready to carry. Perhaps we frighten them. Perhaps they reached out long ago and we lacked the capacity to perceive it. Or perhaps the universe operates according to principles we have not yet uncovered, principles that make the silence not just rational, but inevitable and even necessary. Each of these answers points to the same conclusion. What we do now matters. If we are alone, we are the only voice in the dark, and we must endure if that voice is to persist. If we are early, we are laying the foundations for a future we will never see, but that will be built on what we choose today. And if we are being watched, then how we manage our power, our technology, our conflicts, and the living world we were given may be the very thing that determines whether anyone ever steps out of the shadows and introduces themselves. The Fermi Paradox is not ultimately about aliens. It is a mirror aimed at our own species at the precise moment when we are deciding what kind of civilization we are capable of becoming. And the reflection poses a question we cannot look away from. Do we deserve an answer? Every telescope we build, every signal we send into the dark, every choice we make about our weapons and our planet and the machines we are creating is part of the message we are sending back to the cosmos. The universe provided us with a stage. It gave us intelligence and curiosity, and just enough time. What we do with that time is the only answer the universe is waiting for. The galaxy is listening. What we do next is our reply. And perhaps the most important thing to understand, as we stand here at this particular moment in history, is that we are not passive observers of this question. We are participants in it. The silence is not a verdict handed down to us. It is a condition we are still in the process of responding to. Every generation that has come before us has lived inside this mystery without the tools to test it. We are the first generation that might actually find the answer. The telescopes being built right now, the search programs being designed, the atmospheric analyses being planned, these are not abstract scientific exercises. They are our species reaching out into the unknown with both hands. Whatever we find, or do not find, will tell us something profound about the nature of life and intelligence, and the strange experiment this universe has been running since the first stars ignited. Keep looking up, keep asking the question. Because in a universe this vast and this old and this silent, the act of asking may be the most remarkable thing that has ever happened in it.